Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to continue our discussion on acids and bases. As always, your feedback is more than welcome and highly encouraged, so if you're watching this live, please feel free to drop your thoughts in the chat or call into the show via Discord using the link provided in the description. And if you're watching this as a video, please leave a comment. Without your feedback, I am lost. Alright, so let's go ahead and get into this. This is Acids and Bases, Volume 7. By the way, if you're interested at all in watching Volumes 1 through 6, you can check out my Acids and Bases live streams playlist. There's an image of it right here. There's a link to it in the description. So, okay, let's go ahead and get started. So, I'm going to start things off by just a quick, brief review from the last live stream, which was Acids and Bases Volume 6. So we talked about three main things. The first thing that we talked about was something that I've done several times before, but I wanted to do it again just to make sure that we're all on the same page, which was to find the pH of a weak acid solution. It's a very involved process. What I did was I broke it down into 4 steps. So basically, you write the equation of the weak acid reacting with water. You construct an ice table to determine the expressions for the equilibrium concentrations of everything in terms of a variable. Usually we call that variable x. You build a quadratic equation from that information and then solve the quadratic equation and put that into the formula for pH to get the pH of a weak acid solution. If all that sounds confusing, I covered it in Volume 6. So the other thing we talked about was polyprotic acids. Remember, these are acids that have more than one ionizable proton, right? They can donate a proton and then donate a proton again, having already donated the first proton, right? And we talked about how to find the pH of a polyprotic acid solution. So the example that we went over in the last stream, which was phosphoric acid, right? H3PO4. I'm going to move myself over here briefly. So we can see here that a polyprotic acid, such as phosphoric acid, ionizes in steps, sequential steps, each with their own value of Ka. And finding the pH of a polyprotic acid is actually pretty simple. You can only just consider the first step. The other steps do not contribute significantly to the concentration of hydronium ion and therefore pH. So you're going to do this the same way you would do any weak acid pH problem. You would just ignore the subsequent steps and only focus on the first step. So it's pretty straightforward stuff. pH of a polyprotic acid solution. And then we wrapped things up talking about percent ionization. I'm going to move myself over here again. So percent ionization of a weak acid, pretty straightforward. It's just a formula. Percent ionization is equal to concentration of hydronium at equilibrium divided by the initial concentration of the weak acid times 100%. So really the hard part of this is finding that equilibrium concentration of hydronium, and then you just plug that into the formula, and that gives you percent ionization. We also we did a couple of examples with the same weak acid at 2 different concentrations and calculated percent ionization, and we saw that as the initial concentration of the weak acid increases, the percent ionization actually decreases. So all of that information was covered in Volume 6. So now we're going to get to the topic of tonight's stream. So far, we've talked a lot about acids, right? Strong acids, weak acids, pH of an acidic solution, polyprotic acids, percent ionization of a weak acid, yada, 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 acid, acid, acid. We haven't really talked much about bases. That ends right here, right now. So we're going to be talking about base solutions. And we're going to see a lot of parallels between acids and bases as we talk about bases, because basically the same principles apply. It's just we're applying them in the base direction instead of the acidic direction. So just as acidic solutions can be divided into the categories strong acid and weak acid, bases can also be categorized according to their strength. We have such a thing as strong bases and weak bases. So up here is the general formula. Up here is the general formula for a strong base reacting in the presence of water. Basically, you have the base over here, which is a metal hydroxide. We'll discuss a little bit more on that in the next slide. Reacting, dissociating, dissolving to form the metal cation and the hydroxide ion. So it directly produces hydroxide ion, so therefore it's a base, right? And then if you have a weak base, that is an incomplete ionization. So strong base, that was a complete ionization of reactants to products, and weak bases only partially ionize, which is indicated by these equilibrium arrows that you see here. And when a weak base reacts with water, basically the water acts as an acid. It donates a proton to the base, which accepts the proton and says, thank you for that proton. Really appreciate it. to result in the conjugate acid of that weak base and the hydroxide ion. So we're going to talk about both of these processes in more detail. So we're going to talk about some common strong bases. So we've talked about common strong acids. So these are some of the most common strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide, and barium hydroxide. What do all these strong bases have in common? Well, there's some type of metal hydroxide, and in these cases, it's either an alkali metal or an alkaline earth metal hydroxide, a group 1A metal or group 2A metal hydroxide. And so for all of these reacting in water, they would react according to this general equation down here, where we have the base dissociating to form the metal cation and the hydroxide ion. Now, if that strong base is a group 1A metal hydroxide, it'll, like lithium hydroxide, for instance, this is an example of lithium hydroxide behaving as a base, right? So here you get, it says sodium and hydroxide. I did that incorrectly. You know what? I'm just going to fix that right now because that's bothering me. Sorry about the confusion. I let that one sort of slip through the cracks a little bit. So this is a better way to represent it, right? So lithium hydroxide breaks up into lithium ions and hydroxide ions. And if you have a group 2A metal hydroxide, such as strontium, right? If you have a strontium hydroxide, looks like I did it again. You know, I really need to like proofread these things before I just go live with it. It's like I do proofread them, but I just don't catch everything. There's always like something I miss, right? It's just always something that I miss when I do these things. So, okay. So if it's a group 2A metal hydroxide, you have, such as strontium hydroxide, you have this equation down here. And notice that if you have a group 2A metal hydroxide, such as strontium oxide, you end up getting 2 hydroxide ions in one step. So this isn't like a polyprotic acid type thing where there's like 2 different steps and you behave as a base in each step. No, you're actually producing 2 hydroxide ions in each one of these strontium hydroxide formula units as they're dissolved. So that's going to be very, very important when we're talking about calculating pH and pOH of strong base solutions, right? So we're going to do a couple of examples of this. So we're going to do a couple of examples of finding the pH of a strong base solution starting right about now. So let me move myself over here real quick, and we're going to go to the whiteboard in just a moment. So this is a basic problem, finding the pH of a strong base solution. It says find the hydroxide ion concentration and the pH of a 0.420 molar solution of lithium hydroxide. Lithium hydroxide, of course, is a strong base. So let's go to the whiteboard to solve this one. So if you'll give me just a moment here, I'm going to go ahead and open up the whiteboard, and I'm going to copy and paste the problem in here. And if you have a scientific calculator, I highly recommend busting it out so you can follow along. So, okay, we are copying and pasting that problem in here. I'm going to make it big. Okay, so pH of a strong base solution, 0.420 molar solution of lithium hydroxide. So we know, because lithium hydroxide is a strong base, we know that it's going to ionize completely when you put it in water, right? So in general, with these pH problems, I always like to start with writing the chemical equation for the reaction that you're looking at, right? So the chemical equation for this reaction would look something like this, where we have lithium hydroxide, LiOH, which is aqueous, and that's going to react using a single arrow indicating a complete dissociation, a complete ionization, and it's going to become lithium ion Li+, which is aqueous, and also the hydroxide ion OH-, which is also aqueous. So we can reason that because a complete ionization takes place, right, all of these lithium hydroxide units have broken up, they've reacted to form lithium and hydroxide ions, we can assume that the initial concentration of our strong base is going to be identical to the concentration of hydroxides, right? Because 100% of that lithium hydroxide is going to react, right? So that means that the concentration of hydroxide then, and I'll do this in green, I guess, the concentration of hydroxide, right, is going to be 0.420 molar, right? And so now that we know that, how do we find pH? Well, there's actually a couple of ways that we could do it. We could either use Kw, or we could use the relationship between pH and pOH. So in a previous stream, I pointed out that the pH plus the pOH is equal to 14, right? So that's how these two terms are related. So my personal preference would be to find pOH, and then once you have that pOH, you subtract it from 14, and that gives you pH, right? So what I'm going to do is I'm going to calculate the pOH, right? So pOH is simply the negative logarithm of the hydroxide ion concentration, which of course we just established is 0.420 molar, right? So the negative log of 0.420, what is that? Well, the number that I got was, and again, I'm inviting anybody who's watching this to follow along if you're interested in that. The number that I got for the pOH, not the pH, but the pOH, is 0.377, right? And then we can simply use this formula here, this relationship with between pH and pOH. The sum of them is equal to 14. We can simply use that to find the pH. So if the sum of pH and pOH is 14, then that means that, I'll do this in purple, pH is equal to 14 minus the pOH. And again, we just calculated the pOH. 14 minus going to be that 0.377, right? I used the wrong shade of purple here. 0.377, right? So 14 minus 0.377, that's simply going to be 13.623. So that is our pH, right? So we started by writing the equation. We understood that because we have a complete ionization, that the initial concentration of lithium hydroxide is going to be the final concentration of just hydroxide ion. We calculated pOH, and then we subtracted the pOH that we calculated from 14 to arrive at our pH. So that's one example of finding the pH of a strong base solution. So I'm going to go ahead and delete all of this information, and we're going to go ahead and do another problem involving finding the pH of a strong base solution. So if you'll give me just a moment, I'll go ahead and throw that on the board. And I'd like to also say at this point, while I'm grabbing this problem and putting it on the board, that if you find this stream, this video valuable, if you're finding value in this content, then I would certainly appreciate your support of the stream, whether that means giving a thumbs up on this video, sharing it with people who might be interested, or even sending a super chat. I would wholeheartedly appreciate it. So, okay, so here's another problem in which we're going to find the pH of a strong base solution. And that's actually not the right problem. I just grabbed the same problem and put it right back there. So let me get the correct one real quick. Okay, here it is. All right, this is it. I don't know what happened before, but this is the correct problem. Grab the wrong thing. Back. Okay. So this says to find the hydroxide concentration and the pH of a 8.87 times 10 to the minus 3 molar solution of calcium hydroxide. So just as we did with the last example, I'm just going to start by simply writing the chemical equation associated with the acid-base reaction, right? So we have calcium hydroxide, that's Ca, and then OH2, and that's aqueous. Going to react with a single arrow to form the calcium ion. Calcium is Ca2+, right? Because all those group 2A metals have 2+ charged cations, right? And that's aqueous. And then we're going to have 2 of these OH minuses, 2 hydroxides, and that's aqueous, right? So we understand that there's a complete ionization that takes place. So all of the calcium hydroxide reacts to form calcium and hydroxide. But one thing that we need to make sure that we take into account is, and I'm going to highlight it right here, this coefficient of 2 in front of the hydroxides. So because there's a coefficient of 2 in front of that hydroxide, that means that the hydroxide concentration, I'll go ahead and write this in right here, the OH minus concentration is going to be twice. It's going to be 2 times the concentration, the initial concentration of our calcium hydroxide. So 2 times that initial concentration. So 2 times the 8.87 times 10 to the minus 3, right? So that's going to be our hydroxide concentration. And I got a value of 1.77 times 10 to the minus 2 molar, right? So that's our hydroxide concentration. We can go ahead and get the pOH of that, right? So pOH equal to the negative logarithm of the hydroxide concentration. In this case, that's 1.77 times 10 to the minus 2. So if we perform that calculation, minus log of 1.77 times 10 to the minus 2, we end up getting a value of 1.752. Notice that there's 3 decimal places in this value right here because there are 3 significant figures in the number that I'm taking the logarithm of. That's the rules for sig figs and logarithms. You take a logarithm of something, it has to have the same number of decimal places as the number of sig figs in your original number that you took the logarithm of. So that's correct. And then we understand that pH plus pOH is 14. And so if we want the pH, that's going to be, pH is going to be 14 minus that pOH, which in this case 1.752. So our pH is going to be 12.248. So again, started by writing the equation, recognize that because there are 2 hydroxide ions that are produced per unit of calcium hydroxide that reacts, we had to double the initial concentration of calcium hydroxide to get the concentration of hydroxide ion. We grab the pOH using the formula for pOH, minus log of the hydroxide ion concentration, and then we use the relationship between pH and pOH, the fact that they add up to 14, to arrive at our value of pH. So pretty straightforward calculation, I would say. And again, if anybody has any questions about that, feel free to ask. I am here to help. I'm here to answer any questions that you might have about this stuff. So, all right, we're going to go back to the PowerPoint real quick. I'm going to pull that up. So we've done those 2 problems. So we've talked about strong bases, right? Now let's switch gears and talk about some weak bases, right? And so by weak base, of course, I mean a base that ionizes partially, not completely, but partially when it reacts with water. So these are some examples of some common weak bases. You got ammonia, that's a very common one, NH3. Methylamine, which you might be familiar with from watching a very, very excellent TV show called Breaking Bad. Ethylamine, that's another common weak base. You got pyridine. If you ever worked with pyridine before, it smells horrible. What might be one of the worst smelling chemicals that's out there. Carbonate ion, bicarbonate ion, these are 2 other examples of some weak bases. And for all of these, the general formula at the bottom would apply, where you have the reactants and products separated by the half-headed equilibrium arrows indicating incomplete ionization. You have the base reacting with water. The water donates an H plus to the base. The base says, hey, thanks for that H plus, appreciate it. To result in the conjugate acid of that base, BH plus, as a general formula, and the hydroxide ion. So when we were talking about weak acids, we started to understand that not all weak acids are created equal. Some weak acids are stronger than other weak acids, and there is a way by which we can quantify the relative strength of a weak acid, and that was using the acid dissociation constant. So bases have sort of a similar story, right? If we want to quantify the strength of a weak base, there's another equilibrium constant called the base ionization constant, or K sub B. It's also called the base dissociation constant. It says acid dissociation constant, and that's only because of my horrible ability to proofread what I'm doing. But it's the base dissociation constant. And so the formula for this equilibrium constant would be given right here. And again, the formula for any equilibrium constant is just, products over reactants, right? And so that's what we have here. We have the concentrations of our 2 products, the conjugate acid of the base, that's BH plus, and hydroxide ion. Those are in the numerator of the expression for the base ionization constant. And then in the denominator, we have just the concentration of the base. So just with all equilibrium constants, the larger they are, that means the more product favored they are, the more of the extent to which they react to become products. And if you have a very, very small value of Kb, that means you have a very, very weak weak base, right? Not much of those reactant molecules react to form products, right? So, and again, all of this should be pretty familiar because we've done all of this with acids. It's just we're doing with bases now, but the same principles apply here. So the next slide we're going to look at is just a table of some of those common weak acids that we looked at a moment ago: ammonia, methylamine, ethylamine, and so on. And so the formulas of these weak bases are all shown along with their values of Kb. Weak acids that have larger values of Kb are stronger than weak acids that have smaller values of Kb. And I've also included a column over here of pKb, right? So we can use that same P scale like pH, pKa. We can also apply that to Kb, where the pKb is simply the negative logarithm of the Kb, the base dissociation constant. And of course, by using a logarithmic scale, it's basically a compact way to specify our numbers because values of Kb can have a very, very wide range. Whenever you have a wide range of data, it's helpful to use a logarithmic scale. It keeps the numbers more intact. So instead of comparing all these values up here where we have to invoke this scientific notation, we can just compare these pKb values. It's a lot easier on the eyes, right? And the lower value of pKb is going to indicate the stronger weak base, right? So of all these weak bases listed here, you know, which one of them has the lowest value of pKb? That looks like it's ethylamine right here, right? 3.25 is the lowest value, the smallest value of pKb. And so that would be the strongest of these weak bases. So in the next slide, what we're going to do is we're going to find the pH of a weak base solution. And that's right here. So the problem basically just says to find the pH of a 0.456 molar solution of ammonia, that's NH3, and it says that the Kb, the base dissociation constant of NH3, is 1.8 times 10 to the minus 5. So we're going to use basically the same principle, the same technique that we would for finding pH of a weak acid solution, but we're just going to apply that knowledge and apply those techniques to a weak base. So I'm going to go ahead and take you straight to the whiteboard once again, and I'm going to copy this problem here. Just a moment, find it. Copy this problem here, and we're going to find the pH of a weak base solution. So here we go. So just pasted it in there. Try to give myself enough room here. There's going to be a lot of information here, right? Okay. All right. So again, with all these kind of problems, I usually just like to write the chemical equation for the for the acid-base reaction first. So what would that look like? Well, you would have NH3, that's your base, right? And that's aqueous, reacting with water, H2O, which is, of course, a liquid. Going to separate the reactants and products using the half-headed equilibrium arrows, and the products are going to be NH4 plus, and that's aqueous. That's simply the conjugate acid of NH3. It's what you get when the NH3 accepts an H plus, right? NH4 plus, that's the ammonium ion for anybody who's interested. And we're going to get the hydroxide ion, OH minus, and that's also aqueous, right? So the next thing that we want to do is we want to set up an ice table, right? So the ice table, what that accomplishes is that allows us to express the equilibrium concentrations of every reactant and product in terms of a variable, which we usually call X, right? So I stands for initial, C stands for change, E stands for the equilibrium concentration. So initially we have 0.456 molar NH3. We can assume that the initial concentrations of ammonium and of hydroxide are both 0. There is going to be some hydroxide just in the water by itself due to the auto-ionization of water. Water will produce hydroxide ion on its own, but it does so to a very, very small degree. So because that degree is so small, we can just ignore it from the calculation, right? Now the change, what's that going to be? Well, we know that the concentration of ammonia, NH3, is going to reduce. It's going to go down by a variable, which we'll call X. And then we also know that the concentrations of NH4 plus and of OH minus are going to increase by that same value, X, right? And so at equilibrium, what are we left with? Well, it's basically initial plus change. So at equilibrium, we have 0.456 minus X in the case of NH3. And then for NH4 plus and OH minus, we just have X for both of those, right? So I'm going to resize myself a little bit because I'm kind of a little bit too big for this whiteboard. Let me just slim down. There we go. Okay. All right. So now we're getting somewhere. We have constructed our ice table, and we have used it to figure out the equilibrium concentrations expressed in terms of this variable X. And notice that I haven't done anything with this water because water is a pure liquid. Its concentration does not change over the course of the reaction, and so we omit it from any equilibrium considerations, right? So now what we can do is we can apply what we know about Kb, right? We know that Kb, right, the base dissociation constant, which is equal to the concentration of NH4 plus times the concentration of OH minus, and that whole expression divided by the concentration of NH3, right? Equilibrium constant, just products over reactants, right? We know that that value is equal to 1.8 times 10 to the minus 5. That's just given by the problem, right? And now, using these equilibrium concentrations in terms of X, we can substitute those values into these concentrations that are shown in this equilibrium constant expression, and that's going to help us set up a quadratic equation. And again, all of this should look pretty familiar at this point because this is the same exact stuff that we've done with weak acid solutions, just we're doing it for a base now, right? So what does this look like? Well, NH4 plus and OH minus, those are both X, and so the numerator of this will become X times X. I'll just write that as X squared. And then in the denominator, we have concentration of NH3, which is 0.456 minus X. So now that we have our quadratic equation, what I'm going to do is I'm just going to take the ice table and delete it so that I can make myself enough room to continue the rest of the calculations that we have to do. So it looks like I didn't delete that. So what I'm going to do is I'm going to grab this whole thing here, and if it all goes well, I'm going to drag it. Oh, look at that. Really getting kind of decent at this. I'm going to drag it up there. Okay, so we have this quadratic equation right here. 1.8 times 10 to the minus 5 is equal to X squared over 0.456 minus X. Now we could solve this equation by using the quadratic formula, but I don't prefer to do that. I prefer to take the path of least resistance. So what I'm going to do is I'm going to do the X is small approximation. I'm going to cross this out. I'm going to assume that this value of X is very, very small compared to the number from which we are subtracting it. In this case, 0.456, right? I'm going to assume that this is so small that it contributes negligibly to this expression right here. 0.46 minus X is essentially 0.456. That's what I'm thinking, right? And we can test the validity of that approximation later if we want, but that's what I'm going to do. I'm going to make that approximation. So that simplifies this equation quite a bit, right? X squared over 0.456 is equal to 1.8 times 10 to the minus 5. I'm going to go ahead and erase this stuff over here just to give myself some more room. Now, if we multiply both sides of the equation by 0.456, right, then we will get rid of the 0.456 in the denominator here. So I'll take this X squared and kind of drag it over there so it's all on one line, right? And so we have this X squared is equal to the product of these two terms here. And so to get rid of that squared, what we can do is we can just take the square root of both sides of the equation, and that gets rid of that X squared. And so we are left with X, which is equal to the hydroxide ion concentration, according to our ice table. Now, I just deleted the ice table, but I've done so many of these that I remember it pretty well. And if you're doing this problem, you'll probably write everything out and not delete anything as you go like I'm doing. So X, which is equal to the hydroxide ion concentration, is equal to this whole big term here, where we have the square root of the product of 0.456 and 1.8 times 10 to the minus 5, right? So if you calculate that, right, square root of this product here, what are you going to get? Well, luckily I've done this problem ahead of time, and I got a value of 2.9 times 10 to the minus 3 molar, right? So that is our hydroxide ion concentration. So I'm going to erase all of that and just kind of bring this guy closer. So hydroxide ion concentration is equal to 2.9 times 10 to the minus 3 molar. So we're still kind of a long way from where we need to be, right? We have to find the pH of this. All we have now is the hydroxide concentration. But again, I'm going to do this the way that I like to do them, which is I'm going to start by calculating the pOH, right? pOH is the negative logarithm of the hydroxide ion concentration. So that's 2.9 times 10 to the minus 3, right? That's pOH, negative log of 2.9 times 10 to the minus 3, right? So what's the value of pOH that I end up getting? Well, if I plug this into a calculator, I'm going to get a value of 2.54, right? And then we understand that pH plus pOH is equal to 14, right? So that means that the pH is going to be equal to 14 minus the pOH, right? We just calculated our pOH, that's 2.54, and so this becomes 14 minus 2.54. So 14 minus 2.54, that ends up being what? 11.46. So that is our value of pH. So again, a lot of parallels here, a lot of similar strategies and techniques that we used when we were doing pH of a weak acid. We're just applying them now to a weak base, right? So we started by simply writing out the equation, right? We constructed our ice table. The ice table gave us the expressions for the equilibrium concentrations of every reactant and product in terms of the variable x. That helped us to build a quadratic equation. We solved that quadratic equation to get the hydroxide ion concentration. We calculated pOH from that, and then we calculated pH once we knew pOH, understanding that the sum of pH and pOH is equal to 14. Okay, so that's strong bases and that's weak bases, and that's actually all I've got for you tonight. So for those of you who have been watching, thank you very much for watching. I wholeheartedly appreciate it. I hope everybody has had a great weekend, and I hope you are all geared up to have a wonderful, productive, safe week. In case you didn't know, I stream weekly Sunday nights at 9 o'clock p.m. Eastern time. So if you ever want to drop by and check out what we're talking about, you'd be very, very welcome. So, all right. Thanks again, everybody. That's going to do it for tonight, and I'll see you in the next stream. Take care.